So this lesson is going to be about inverse functions, and it's going to include two sections from Newton, 13.3 and 13.4. I try and make the sections pretty small so that they're manageable bites. So earlier we learned about 4 different ways to represent a function. So let me do a quick review. A map, a set of ordered pairs, a graph, and an equation. So for each of those 4, we're going to go through a quick review of the types of representations of functions and then also of how we look at inverse functions through that lens. So the first way we looked at functions was with a map. We said you can make a map with a table of data, and the domain in this case can be states, and the range can be numbers that represent the population in millions. And then for this second example, the domain is kinds of animals, and the range is the life expectancy. And then we talked about that in order to be a function, you have to have each guy in the domain has somebody that they match to in the range and just one somebody that they go to. So the first map is obviously a function. The second map is also a function because each animal has a life expectancy and has only one life expectancy. So then we go to the set of ordered pairs, and we have 2, 6, -3, 6, 4, 9, and 1, 10. So I like to make maps for these also. And we would have that the domain is the x coordinates, 2, -3, 4, and 1. And the range is the y coordinates, 6, 9, and 10. And then we see that 2 corresponds to a y coordinate of 6, -3 corresponds to 6, 4 corresponds to 9, and 1 corresponds to 10. So each item in the domain has an item it corresponds to in the range and has only one item in the range. So this is how we decided it is a function. So then a graph, if you have a graph, we've seen lots of graphs of functions. I think it's a really common kind of misconception that a graph is a function. But a graph is just one way of representing a function. It's a picture of a function. The function is actually the rule that says how to find corresponding y values for each x value in the domain. And we had the vertical line test for deciding if something was a function. If everywhere you draw a vertical line, you touch the graph only once, it's the graph of a function. And then we had equations, which is probably the most familiar way of seeing a function represented. So we started out by looking at maps, and we said as long as each item has one price, we're good, but if one item has more than one price, then this is not a function. Because if somebody brought a soda up to the cash register, we would not know how much to charge them for it. So then we looked at an example that was a function, and it was okay for more than one item to have the same price. This is still a function. But now we're going to be looking for one more condition. We're going to say, can you tell what you bought from the receipt? So let's make a map. And this is a function. Every item has a price and has only one price. And then because if the receipt said 79 cents and 99 cents, I could tell what you bought. This function is 1-to-1. So to be a function, we have to meet every item has a price and every item has only one price. To be 1-to-1, you are adding the requirement that each price corresponds to only one item. So let's back up and look at the second example we made. This is a function, but it's not one-to-one, because if the price 89 cents was on the receipt, we would not be able to tell what was purchased. Okay, so we're talking a lot about one-to-one. Let me scroll down here really quickly to get to what's the point. If a function is one-to-one, it has an inverse. So that's our goal here. We're talking about inverse functions. So let's back up and do some more work on that. So a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the domain. I said that wrong, in the range. So if x1 and x2 are two different inputs of a function, then you can't have f of x1 equaling f of x2, so they can't have the same y values, or you won't be one-to-one. So we looked at a visual way to tell if a function was one-to-one using a map, but what about some of the other ways? So what if the function is presented as a set of ordered pairs? Well, let's look at it in the arrangement of a map. So 2, -3, 4, and 1 are our domain items. 6, 9, and 10 are the range. 2 corresponds to 6. -3 corresponds to 6. 4 corresponds to 9. And 1 corresponds to 10. So this is a function, but it's not one-to-one. Because if something cost $6, we would not be able to tell what item it was that you bought. So now we're going to talk about a theorem for use when you're given a visual representation or graph of the function. If every horizontal line intersects the graph of a function in at most one point, then f is one-to-one. Okay, so if the graph looks like this, clearly I can draw a horizontal line that touches it in more than one point, and so this is not one-to-one. Okay, if the function is presented as an equation, it can be pretty challenging to determine whether it's one-to-one. So you'll learn that later in a higher level course. It involves really a proof that you have to do, and so I didn't want to get sidetracked into proofs. But I do want you to think about this. Do you think that a function that is always increasing or always decreasing will be one-to-one? And I'm asking you to justify your answer because one of our desired outcomes is that you will get better and better at expressing your mathematical thinking in a clear way for someone else to be able to understand it. So I would suggest that you pause the lecture here and think about this. Do you think that if your function is always increasing or always decreasing, that that is enough to guarantee that it's one-to-one? So I'd suggest drawing some examples. So think about what a function would have to look like if it's always increasing. So this is a function. It passes the vertical line test. It's one-to-one. We can see visually if we imagine doing the horizontal line test. But it's always increasing. So think about if I have x1 smaller than x2, because this is always increasing, then it would have to be true that f of x1 is smaller than f of x2 because we made the requirement that the function is always increasing. So if you look back at this requirement, it says x1 and x2 are two different inputs and the function's one-to-one if the outputs are not equal. Well, we have shown that the outputs are not equal. In fact, one is smaller than the other. So this is an informal proof, but think about why it's true, and we'll be using it again later. So it's actually a theorem that if a function is strictly increasing, it's one-to-one. Or if it's always decreasing, that's one-to-one. And this idea will become very useful when we talk about exponential and logarithmic functions. So why do we care if a function's one-to-one? It's because there is higher level math work that guarantees us that if a function is one-to-one, it has an inverse. So if somebody tells you this function is one-to-one, please find its inverse, the answer will never be it doesn't have one. Okay, so in order to undo the effect of a function, we needed a function that has the opposite effect, an undoing function. So you already know a lot of these. If you think about the square root function and you want to undo that, then you square. If you have the cubing function and you want to undo that, you cube root. If you think about even something simple like adding and then subtracting, those undo each other. Multiplying and dividing, those are inverse operations of each other. So in math, for whatever reason, they don't use the word reverse, they use the word inverse. So the function that undoes what the first function did is called its inverse. So suppose that f is a one-to-one function, then corresponding to each x in the domain, there is exactly one y, and corresponding to each y, there is exactly one x, and this is because the function is one-to-one. The correspondence from the range of f back to the domain of f is called the inverse function of f, and we write this in symbolic language as f with a superscript -1. So that's not an exponent, and it's just a symbolic language that gets used to represent the inverse function. So let me draw you a little picture. This is one of the ways I like to think of function and inverse function. So we have the domain and we have the range. And then we have this function f that tells us how to find the corresponding item in the range for a particular item in the domain. Well, then if we apply the inverse function, we go back from the range of f to the domain of f. So here is a map representation of a function, and each way of representing the function has its own way of finding the inverse. So the domain of this function is states, and so I'm just going to use the first letter because they're unique, so you'll know which state I'm talking about. So the domain of the function is the set of these 5 states. And then the range of the function is these population numbers, 6.2, 6.1, 0.8, 8.3, and 5.8. So then we know that the domain of the inverse function is the range of the original function. The domain and range have switched jobs in effect. So if we're mapping back the other way, that's f inverse. So then the range of the inverse function is the same as the domain of the original function. So I'm going to pause here just so the video doesn't get too long and then finish in a second video.